Good to go. Okay, much winking for Ursula. So today I want to take the opportunity to tell you about some of the recent work that we've been doing with the adaptive particle refinement, which is a really nice way of saying I haven't done anything useful in the last year, so I'm going to talk about other people's work instead. Thanks, Ursula. That is not, can we go back? One, thank you, tap. So for those of you who don't know, adaptive particle refinement is analogous to adaptive mesh refinement in grid codes. It's just a way for us to locally increase the resolution in a pocket of your simulation. So the idea is that you have a region, I always think of it like an onion in your simulation. You say right there, I want to have higher resolution, or even lower resolution, depending on your need. Higher resolution or lower resolution, that means you need to use a different number of particles to describe the same density prescription. And so to do that, what we fundamentally need to have is a way of changing the number of particles that you have as they're moving through the onion, is the way to think about it. If you have particles moving from low resolution to high resolution, we need a method to split them, which is what we see on the left-hand side. So you have your low resolution particles on the left, they move, they cross the boundary into a high resolution region, they split into lots of children particles. And the alternative on the other side is if you have particles moving from your high resolution into your low resolution, you need to have a way to merge them or to de-refine them. And so here what we do is we use the KD tree of Phantom to pair the particles up to ask the question, is the pair of particles across the boundary? If it is, then we go ahead and we merge them and we average the properties. And that's fundamentally all that's really happening in Phantom. It's really exciting because it allows us to do a bunch of different things that we weren't able to do before. As a first case kind of scenario, an example of what we can use it for, thank you, Ursula. One of the best tests I think that we had in the paper was this flyby scenario. So it's inspired by some work by Jeremy Smallwood that we were involved in, and he had a star, a disk around it, and another star come and have a gravitational interaction with the disk and the star. And what happened was he was really interested in the disk that formed around the perturber star. He was interested because as that perturber star comes in, it can capture this material and form its own disk. And he was looking at the orientation of that disk with respect to the original primary disk. So what we did was we repeated his calculations and we put this pocket of high resolution around the perturber star and we let it track that perturber star as it was going around. Thank you, Ursula. And so, yep, next one. So to show you this, in the middle, I'm going to show our APR simulation, but for comparison, on the left-hand side and the right-hand side, we bookended it with non-APR calculations. So just regular, everyday Phantom. The difference between the left and the right-hand side is the number of particles, the resolution. So between the left and the right-hand side, we've doubled the spatial resolution, which corresponds to a factor of 8 in particle number. The movie here is centered on the perturber particles. So you see the disk coming past the star rather than the star coming past the disk. Thank you. And so the test for our simulation, for our method to be working, is going to be if the middle panel looks like the far right-hand panel. Because locally they have the same resolution around that perturber star, but we're getting that for a much lower number of particles in total. So here with only 6.4 by 10 to the 5 particles, we get the same evolution around the perturber star as a simulation that cost us 4 million particles on the far right-hand side. So qualitatively, we have lots of evidence to show that this method is working exactly the way that we expect. Thank you, Ursula. And quantitatively, we can say the same thing. So in this paper, to try and measure the accuracy of the APR method, we looked at the mass of the sinks as a function of time. So here you have there's the 2 sink particles, but here we're plotting what the perturber star is doing. And the reason that we use the mass is because the accretion rate onto that sink particle depends very sensitively on the resolution and the disk viscosity and all of those kinds of things. So if we got any of that wrong, the mass as a function of time would be quite different. The low resolution simulation is shown by this purple line up here. The high resolution on the right-hand side is shown by this beige line, which might be a little bit hard to see. And our APR simulations, we did a few varieties of these, are all lined up on top of what that high resolution simulation is doing. So quantitatively, we can also say that the APR is doing exactly what we expect. Thank you, Ursula. So we can quantify exactly, as a metric, the difference between our high resolution reference case and what the APR is doing. We take that as percentage difference to calculate the error, and the maximum of that is the error plus our simulation. So for our flyby simulation, the error is of the order of 10 to the negative 4%, it's actually negligible. We ran some other tests, so we had a planet disk interaction and a circumbinary disk, and they get errors that are kind of the same. The planet disk interaction one, I'll note, is a bit higher, and we're going to come back to that. We also found this quite a speed up as well. So we were kind of talking about this in the context of Jack's work, like, is it actually faster to use the API, yes or no? The speed ups that you have here, it's up to a factor of 6 or so. That's with the kind of old version. Tim of Shamrock fame helped us to actually speed up the API. So this is now a lower estimate. The API is much faster than it used to be. The other benefit you get is that it costs you a lot less, like in terms of the storage. So for those of you who are like, you know, there's very limited storage on your cluster, if you're using the API, because you're using fewer particles, you can actually store more stuff, basically, which I think is very helpful for lots of people. Thanks, Ursula. So I want to talk about some of the applications that API has been used for since last year. Daniel's already touched on this work by Fitz, which is absolutely fantastic. So she was trying to demonstrate that, like, what resolution do you need to use in order to converge the nozzle shock, the behavior of this star as it's split into this stream and it comes past the black hole the second time around. And to get to these 16 levels here, this is the global equivalent resolution of 650 billion particles, which is something we couldn't do with Phantom before, but it's something we can do using the API. Thank you. And Daniel's already shown this graph. And so the point here is that you really can get convergence for this particular problem, but API is the way to do it. And I think it was 16 levels of refinement to get there. Thank you. Okay, but the other quiet thing that happened in Fitz's paper that I think is really important, we should highlight, is she worked out a different way to place the particles when you split them. So in the original implementation, what we did was you have your regions of the API, your layers of the onion that you can see on the top right. And we always place the particles when we split them tangential to the boundary. That was because we didn't want particles to accidentally slip backwards across the boundary they had just crossed. But what Fitz found was that this is terrible for a tidal disruption event because the stream is basically going perpendicular to the shells of the API. And so that meant that stream split, like it widened when it wasn't meant to, but also that changed the energy, like the orbital energy of the particles, which is disastrous for a tidal disruption event. So instead, she found a way to split them along the geodesic. And so not only is the API compatible with GR, but we now have like a much better way for some problems for how you should be splitting your particles, which I think is really cool. Thank you. The other development that's in the works right now is in the code, sorry, the version of the code you can pull right now. API is compatible with MCFOS, thanks to some work by Jose Faria. So he was coming at this problem from an entirely different perspective. So he's doing circumbinary disks as well. And his problem was that he couldn't afford more particles. On the computational resources he basically had a cap for the number of particles he could use, and he knew that wasn't enough for the problem that he's simulating. He's looking at the luminosity that you get in a circumbinary disk from the stars if you include the accretion luminosity onto the stars themselves using MCFOS. So by using API, he was able to resolve the innermost part of this system much better, and he knew he needed that in order to get the physics right for his particular problem. And that meant that he was able to calculate, he sent me this graph this morning, this is the bolometric luminosity across the course of his simulation. And in the blue line, he's including the radiative transfer, but he's not including luminosity from the stars. And in the red line, he's including luminosity from the stars, and then the yellow line is beefed up in some way. And what he's been able to show so far with these tentative results is that the luminosity from the stars is actually the most important for what we're looking at when we're observing these particular systems. Thanks. The other thing I think that's worth talking about, again, this is happening really quietly kind of in the background, is that you can use the API to like take one of your dumps from your simulation and just beef up the resolution across the whole thing. You don't have to have like a little onion going through your simulation. You can say, do you know, I want the whole thing to either be increased in resolution or alternatively decreased in resolution. And this is really important if you have some kind of a process in your simulation that strips most of the material or accretes a lot of material, and you're left with like 20% of the particles that you started with, and you can't avoid that process. You can stop your simulation, you can use the API to do this, and you can increase the resolution drastically and then just carry on your simulation. It's actually a mod dump kind of a feature. It's called split part. This was first used by Christoph Kant, and the reason that he used this was he was generating these synthetic observations, and he wanted the surface layers of the disk to be more highly resolved. So they beefed up the resolution, They ran it for a couple more orbits, and then they took the synthetic observations to improve the resolution. So this is something else you can do. It's available in the code right now. Thank you. The thing that I want to finish on is stars. Liang is going to speak next. I hope very much about this. So I don't want to say too much about it, but the premise is that when you're trying to simulate these stars in hydrostatic equilibrium, this is the base thing you need to do in order to understand like common envelope calculations and all this kind of thing. When you're doing this, the problem is that we care about what the surface of the star is doing, and that's the worst resolved part of your calculation. So the APR is an excellent application for this exact problem. And what we want to do is to have the outermost layer more highly resolved and the inside of the star lower resolution. But I joke about this, but I'm very serious. We have a working algorithm, and with the confidence of a man, I said, let's just do it. It will work. Thank you. And it did not at all. So the first thing you notice is that our star moves away from the center of mass. It like actually wanders around in the simulation. It's a little bit hard to see, but the density structure changes dramatically. And also at the start of the calculation, there's a terrible transient that looks a bit boxy and like squarey with corners, which is also terrible for SPH. Because this star is just meant to be in hydrostatic equilibrium, not doing anything else, the fact that it's moving around like this tells us that we've broken conservation. Thanks, Ursula. And indeed we did. So these plots here, the actual content of these is not as important, but they're showing all the things that we would like to normally conserve in SPH, and that we use SPH because we want to conserve these things. Thank you. The light blue line is showing our reference calculation with no APR. So this is what we're aiming for. We want to match. And the dark blue line is showing you what happens when we use the method that's currently in the public code for this kind of a problem. And you can see in particular that we don't conserve our total energy at all. The center of mass moves dramatically, and the angular and total momentum are not conserved in the slightest. Thanks, Ursula. And the problem is this. If you merge two particles into one particle when you're doing this merging procedure, you don't have enough degrees of freedom to simultaneously conserve linear momentum, angular momentum, and kinetic energy, let alone entropy and all of the other things. You just don't have enough. So what we're trying to work on at the moment is a way around this that I'm calling magic merging, because if it works, it will be magical. The idea is this. You have your high resolution particles. They're going to move into the low resolution region. Thank you. And instead of merging two particles into one particle, we're now going to merge 12 particles into 6 particles. Thank you. And so instead of boxing up groups of 2, we box up groups of 12. Yeah. And the first thing we do across our group of 12 particles is we calculate the quadrupole moment. The way to think about this is a metric for where the mass of the particles is, those 12 particles. Thank you. And then we move to a frame that is decided by the eigenvectors of the quadrupole moments. And then, thank you very much, we place our new 6 particles onto these eigenvectors. This sounds like a really complicated thing to be doing, but the premise is by doing this, we have automatically conserved where the mass of the particles is distributed, which means that we should do a fair job at conserving the density. And by having 6 particles as what we're merging into, we can place them symmetrically across these eigenvectors. Thank you. The next thing we do is, okay, well, we've decided where the particles are. We then can set the velocities of those particles to conserve angular momentum. You can see that the velocity pairs that we have across the pairs, they're opposing, which means that you get a lovely little angular momentum conservation there. Thank you very much. The next problem that we have is kinetic energy, right? You've already set the positions, you've already set the velocities. Kinetic energy is just a half mv squared. So what do? We calculate the kinetic energy we have from the velocities that we require to conserve angular momentum, the velocity we've already applied. We then say, okay, well, does that match the kinetic energy we know we need from the original 12 particles? If it doesn't, we add a small bulk velocity to the group of particles that then matches the difference we need to conserve the kinetic energy in total. Thank you. Then we move back to the simulation frame. The thing I haven't written on the slide is that we also try to conserve entropy. When we do this procedure, we record the entropy that we should have across the 12 particles. This all happens in the update API routine. Particles go through dense. Then we re-prescribe the pressure and the internal energy so that we should be conserving entropy. Thank you very much. with this new, and if you press play, it should play them. Thanks, right. With this new method, it's not perfect, definitely not, but it's way better than it was before. So it's a bit hard to see on the screen. The star center of mass doesn't move very happily. So we're looking at the dark purple line is our new method. It's a little bit different. It's not exactly perfectly conserved, but it's much better than it was before. In terms of the total energy, we still don't conserve that quite right just yet, but we do conserve things like the angular momentum, the total momentum, and the kinetic energy. We do a lot better than we were doing before. So this is still a work in progress. The other thing you'll notice is that at the start of the calculation, the density, particularly at the edge of the star, it shifts out a little bit. It kind of expands a tiny little bit. And that's something also we're trying to work on as well. Every time we get something conserved a bit better though, the density profile improves as well. Thanks, Ursula. And so, just to finish up, in the last year or so, the first thing that we've got is some new split directions thanks to FITS. The other thing that happened as a result of the workshop last year is multiple regions. I had some people asking, can I have multiple APR regions through my calculation? That's now available, but to my knowledge, nobody is using it. It's there. The APR is now compatible with MCFOS. This is true both in the live calculations and in post-processing if you want to make a synthetic observation, for example. We did the speed up with Tim, which actually made it much, much faster. You have this mod dump that you can use that Christoph used in his work to increase or decrease your global resolution. And the things that I'd love to tackle this week, for anybody who wants to help me out, is this conservative merging, the magic merging that we've been working on for these stars in hydrostatic equilibrium. For the dust, so I talked with Davide earlier in the last week about getting the APR working with these simulations that have this nucleation, but also regular dust. So APR at the moment is not compatible with the regular dust in Phantom. The other thing that I'm really interested in, is some new tests for the APR. At the moment, the tests we have are quite minimal, and what that means is that sometimes problems propagate through the code. We don't want that. So we want to try and design some new tests that are a bit more rigorous than what we currently have. And I'd love to hear ideas